is a very very special field in the industry of VLSI design industry. And maybe if you are in your bachelor's or in your diploma, in the beginning probably you might be thinking design for DFT means maybe discrete Fourier transform, but yeah, that was the case when we were doing our bachelor's. That time VLSI was coming as a very it was very in the early phase of the evolution, and that time maybe we are not that much familiar with this specialization. So that's how special this feature like this field is. Okay. So now I just wanted to give a basic overview of the design. Basically, how do we what are we going to cover today? So in the whole discussion today, I just wanted to mention that so that we in this presentation we are going to I'm going to give the background before what we start. Okay. On the concepts of design for testability. I just want to give a background and then we will go from there, and it gives you a feel like how this specialization design for testability evolved from the basic chip design till how it is currently. Okay. As part of this presentation, okay, we are going to discuss like what are the various building blocks of a chip design. Okay. What are the components that will be part of the in general a chip design. Okay. And then we are going to see what are the like where are different ways how to verify that, and then what are different techniques we have to implement in the design so that any issue in the design will be taken care as part of the production test or any debug. Okay. And then we'll basically come to a discussion point where it gives you indication that okay, this to do all these special kind of things to do this quality test of the design, it needs a special the specialization design the VLSI design, that is called design for testability, and then we will discuss summary. Okay. So I want to cover what are the basic building blocks in a logic design. Okay. Okay. In a design generally, right, not only any design, it need not be a VLSI design, it can be any application. It needs some basic inputs, and it will be a processing logic will be there inside, and it gives output, correct. So to make all these operations happen in a chip, right, what are the different building blocks it constitutes, that is what we are going to discuss. Okay. This picture, if you can see, right, it is a kind of a chip. It can be in a square, it can be in the rectangle. But if you see here the chip boundary, and there are some special components in the green color, and then there are some in the violet color, right. So those are called pads. Okay. For this, assume this is a system, this box is a system, it has inputs from the external world interfaces through the pads. Those are input pads that are in the green color, and output pads or bidirectional pads, you can say, those are in the purple color. And so these are basically the basic interface that will interact with the external world, okay, with the what is happening inside the building block, which is chip. If you see in the chip, right, it contains the standard logic, okay, that is one of the main component of the design, and then other important components are the memories. Okay. So these are three basic components in any design that makes the chip. Along with that, there will be more complex components such as PLLs or voltage regulator, power switch. There are many components, but for simplicity we can assume that okay, these are the three basic components. One is pads, which is IO. Second one is the standard cell logic. We will discuss what is standard cell logic later. Okay. And third one is the memory components. Okay. Now we will discuss about the first component is IO, which is input output, right. There are various types of IOs as we discussed in the beginning. One is input pad, and the other one is output. Output can be regular 2-state output, or it could be a 3-state output. 3-state means 0, 1 and Z, that is the third state. Okay. And then we have the in-out type. In-out means it can be input output based on the out enable signals. If you see here, even for input also we can have enable, just to make sure that okay, we can allow data or not allow into the design. That's what you see in the top, right. So here if you see in the diagram, assume the left hand side is the internal of the chip and right hand side is the external interface to the chip. that is called pad. Okay, that is the pad port. So if you see data is coming from the chip, and that data, what is, let's say here O data, right? The O data, that is output data, that is going to the external world only if the output enable is high. Okay, if output enable is not high, then the pad will be in the Z state, which is high impedance state. Same thing, input, let's say some external world is driving the input onto the pad, and if you wanted to allow to the chip inside, right, then the input enable has to be high, then only the data can go into the chip. Okay, that is basically the IO pad. These are the basic components of the IO pad. Okay, now just understand, okay, these are the basic building blocks for the input, I mean like for the pads. Okay, here if as mentioned in the description, right, pad types, there are 3 pad types, and then the pad pins contains the input data, output data, and the enables, which is like input enable, output enable, right. And then we will talk about standard cell logic. Okay, this is standard cell logic. Why it's called standard logic, I believe you might be aware, right. There are many other components that we will in the VLSI world. This standard cell has special a place. Why they are called standard cells? Because there are many other complex cells which are not called standard cells. Those are we call like HIP. HIP is like a hard intellectual property. Those we cannot call as standard cell. Okay, standard cell means the basic primitive components. Okay, which can be like basic gates, right, which are AND, OR, inverter, NAND, NOR, right, XOR, XNOR. These are all the gates which are called combinational standard cells. And then other variety of the standard cells are the sequential elements, which can be latches, right, flip flops. These are the sequential elements which are also called standard cell elements. Okay, so if you see this diagram, it is, I believe you understand, it is a circuitry of full adder, right, where the inputs A, B, C, right, A and B are the inputs, and then carry in. So based on these inputs, right, so it is based on the inputs of this logic, the sum is like exclusive of A, B, right, and C, that is a sum, total sum, and then carry will be the whatever logic that mentioned here. So this is the basic simple circuitry which explains that, okay, these are the standard cells that are used to make the circuit designed, right. Yeah, here is not, the flops are not mentioned here, but yeah, you can understand that this is the basic implementation of the logic using the standard cells. Okay, now third important component is memory cell, right. So what is memory cell? So if you understand that any element that stores the data, right, for some time until it is erased or updated, that is called a memory cell, right. So how it is different from the flip flop or latch and flip flop are also memory elements, but how it is different here is, I think is clear, right, from the diagram that, okay, so it is like a compacted version of those flops or latches put together for various reasons like performance, area, and all those reasons. They are put into a single place, okay, that makes the memory cell. Okay, and this memory cell contains the inputs, right, to write into the memory cell. Memory cell, if you see, right, it is a group of memory flip flops add in the order of in a matrix form, you can think of, right. So when you wanted to write data, so the data will be written sent on to the memory, and then clock will be given. Clock is basically the signal that basically sequences operation, right. So along with that, the enable, when you assert it, it is going to write into the memory, that is the write data, right. So and similarly, when you want to read, you have to give read enable, and the address which you want to read from, that's how it's going to be, is going to put the output and that output data. So those are the basic input outputs, and then what are the control signals that are constituents of this memory cell. Okay, so these, yeah, it covers, now we covered input output pad, and the second one is the standard cell logic, and then basically the memory. These are the basic components for making a design, VLSI design, right. And what are other than these, right, in general, chips contain many complex components which can include the clock generator, right. Now as we just now discussed, clock is one of the important control signal, okay, that enables the data like sequence of operation in a design. For to make the sequential system operate properly, clock is the important the element of the design. So it can be having a different frequency, like it can start from kilohertz to gigahertz also, and to generate this clock, we will, because frequency is so high, gigahertz also, So that gigahertz frequency we are getting from external world, it will not be possible because the pads what we discussed will not be able to sustain whatever the timing that is required, right. So what generally is done is internal to the design there will be a on-chip crystal and there will be a PLL, a phase lock loop element, where given the input reference clock to it and it can generate the frequency whichever we want in gigahertz frequency, right. The logic will be there inside the PLL, it will give us whatever frequency we want based on all the multiplication division what is happening that is going to happen inside the PLL, right. And then the voltage regulators, power switches, on-chip fuses, sensors. So these are all very general components that will be part of the any chip design along with the whatever discussed basic elements. Of course, most of these components, right, these are also made up of the standard cells, but they are like they will be part of this IP we call intellectual property, right. It is part of these big IPs. So sensors, maybe just to give a basic background about sensors, right. So sensors can be for thermal sensors or they can be the process sensors. So there are a variety of sensors that generally will be put in part of the design, so that the system can know, for example, temperature sensor, right, sensors. So when the system knows, okay, this is the temperature of the design because what are the operations that's happening in the chip, right, there can be the fans or coolers enabled accordingly, otherwise the chip will be burnt out. That's so that's one example. That is one example of a thermal sensor. Others, for example, when you wanted to see, right, how fast the chip is working, right, there can be a process sensors as well to see or characterize the product, or bin it means put into different bins of the based on their speed, they can be put in different bins. So to see what process this chip corresponds to, there can be a process sensors in the chip. Okay, that is one example of sensor. Okay, now we discussed all the elements that are going to make the chip, right. Now to make a chip design, what are the different steps that are generally taken in the process of chip implementation? What we are going to just give a glance. Okay, right. Any product conceptualization generally happens with some application, right. So for example, right, in the house we will have mechanical switches, right, electrical switch for example, right. So if you wanted to do a remote switch from wherever you want, right, so that is one application. So based on the market requirements and the return investment thing, right, people will conceptualize the idea and then make out of this application they will prepare basically a proof of concept. Okay, if the proof of concept makes worth implementing in a chip, then that will be like a initial point to start the project kickoff, right. Once the project kickoff happens, then comes like this idea, we have the idea and then concept is there. So now what are the different components that we need to be implementing, that comes the chip design planning, right. So for example, in this example of remote switch for the electrical switches in the house, right. So what are the different components you might need, so that all will be designed or defined during the architecture phase. Basically planning is one thing, so then comes the architecture, right, to make this device happen or to get executed. What are the different components we need and where to place them, what are the different interfaces, user interfaces, system interfaces we need to put. Those are all going to be discussed as part of the architecture definition. Once the basic building blocks of this design are understood and once it is finalized where they are going to sit, like block A, block B, block C, how they are going to interact, right, those will be placed first, the design in the basically on the, you can say, floor plan, right, what in the wherever we are going to put fabricate the chip. Okay, that will be having some area, it will have some, it will constitute some area that is called generally in terms of physical design we call this a floor plan, right. In the floor plan where this interface, which interface of this design is going to sit where. So that comes, assume these are like 10 building blocks. So to make this design we need 10 building blocks where each block will sit. So based on interaction they will decide. That is where architecture comes into picture. So once the architecture is finalized, means like, okay, once we confirm that, okay, this block is going to sit in the left side on top left and then it is going to interact with another partition, another block. So that other block will put together close to the bottom or like adjacent to it. So that once that is defined, right, now what is going to go inside the blocks is where the microarchitecture comes into picture, right. So how the functionality of the block will be implemented, that will be defined in detail in the microarchitecture. Okay, so this is all basically the spec. Okay, now this spec will be, next phase of the implementation will be Once the spec is available, this is macro spec is available, then it will be converted into the RTL design. Okay. RTL design, as you are aware, it can be written in the hardware description language. It can be VHDL, it can be Verilog. So these are two languages, I think, and then we have system Verilog. These are the like advanced language right now we have. So all this specification is abstracted into the languages that is called RTL design. Okay, and this is in this language there are more tools like EDA tools that those tools understand and process it in the process of converting these abstraction into the gates and then to the transistors. So there are different levels of abstraction, and to make that abstraction taken care in the process, we need this kind of languages or tools, right. So in this design phase, the whatever spec we discussed, right, the macro architecture spec of a design, that will be converted into the RTL code. Okay, that RTL can be in the VHDL, Verilog, and system Verilog. Okay, once this design is implemented in the Verilog, right, now we wanted to make sure that okay, it matches with the spec whatever we define, whether it will match or not, because there can be errors in the coding, because whatever the expertise people have, right, if there are any issues in the coding, it can fail the intent, right. That is what is taken care during the RTL verification. Generally design will be done by one team, verification will be done by the other team. Okay, but both of them will know what is the intent of the specification, right. If the same person does design verification, it is a high chance that it may not be well qualified verification, right? That is why generally they will be given to different teams, but both the teams will be knowing the spec. Okay, that is the verification part. So, and this verification is like a continuous process as we discuss further. Okay, then comes the physical design implementation. So now till now we discussed about the RTL code, right. Now the code will be converted to the gates. So this is going to happen in the physical design phase. It can start from synthesis and then physical implementation, and then basically it will go through the rigorous process of timing checks, basically, right. To meet the delays between the, let's say, two flops, there will be logic, and see whether this logic is able to meet the timing of the target frequency, right. Because since we are planning frequency of gigahertz, whether the logic that is sitting between two flops, whether it is able to meet the timing to meet the frequency. So those things will be checked as part of the timing sign off. That is generally called static timing check, and okay, that is called static. But same thing we can do dynamic verification also. That happens in next phase, where that is called gate level verification. Okay, so this gate level verification can happen without timing and with timing. Generally for the final sign off, we do with timing. With timing is with the delay annotated on the chip, the gates will be verified with the functional vectors, or it can be scan vectors, right. All this that is part of gate level verification. So once the gate design is properly implemented, verified functionally, verified from the physical design aspects, and verified from the timing aspects, when everything is done, then goes the tape out. Okay, that is the final phase of the design actually. Okay, this is all till the pre-silicon we are talking. Okay, so as I clearly mentioned before, right, in the previous slide, there are multiple steps. Design is an important step, but along with design, verification is a very important step, right. So and verification is a continuous process. Wherever there is a change that we are making into the design, right, that is where we have to do verification also, to make sure that nothing is broken, right. So in the general terms, we can divide this verification to 3 steps. One is logic verification, where it will confirm that okay, functional spec intent is met here, we are not deviating from the functional intent. That is logically it will check okay, everything is fine. Then comes the physical verification, right. Where physical verification means okay, logic is perfect, but now we implemented the design. For example, let's say there is a AND gate, there are 2 AND gates driving another AND gate. Okay, this output of first 2 AND gates will be going as inputs to the second AND gate. Okay, now between the 2 wires, the output of gate A and output of gate B, when it goes to gate C, whether is it going in the right distance, or is it going the space between these 2 wires is sufficient, or is it very close, right. Those are all the things will be checked as part of physical verification. So why do we need to check all this? Because this physical implementation is tied to a process called foundry process, and it will have some rules. If the wire spacing is not followed according to the foundry rules, right, then during manufacturing the 2 wires can get shorted also. We can see some break or short. So these kind of, to make sure that we don't see that kind of problem, right? All this is taken care during the physical implementation and verification. So that is the physical verification, right? And then comes the timing verification, as we just mentioned, discussed in the previous slide, where the static timing check is what is the verification here. We ensure that, okay, this particular design is going to meet the target frequency of the particular, let us say, because the design can contain multiple clocks, and each clock may have different frequencies, right? So let us say from the external world the data is coming into the chip, we have to ensure that the data is properly latched into the design at the right frequency, and internal to the design the data has to be processed, and we have to ensure that the flop to flop timing is properly met according to the frequency. And when the we are sending out the data to the out of the external to the chip, right, we have to ensure that the receiving chip, right, or receiving system will be able to capture the data in the right time. So to ensure that, there will be again timing check we have to do on the output side. So they are all basic verifications at different stages. One other verification also generally, that is called logical equivalence check, right. This is also one verification where wherever you change the design, we have to ensure that the functionality is not broken, okay. That is called logical equivalence check. That is also one of the static check, okay. All along with the static check, so timing is one static check, and then logical equivalence check is one static check. The other one is dynamic check, which we discussed. We are going to verify the design on the gates to ensure that even the dynamically with the test vector, the test is going to pass. So these are all basic verification that we do in the pre-silicon, and then once we qualify that, okay, everything is fine, then only we can tape out, because any issue in this, right, it's going to be very expensive. Once you manufacture chip and find out that you catch the problem post silicon, that is very it is going to be very costly affair to fix the problem, because you have to do again retape out, or there is something, a simple fix there is called metal fix, but any change is going to add up costs, right. So the longer you find the issue, it's going to take more and more cost. So that's why the pre-silicon verification is very important, and it has to be done with utmost care. Otherwise, we'll be having multiple releases of the same chip, and that's going to cost the company very in a dear way. Okay, now till now we discussed about the pre-silicon verification, right? And then once the chip is manufactured, so then we can, if everything is perfect, right? And if you make sure that the pre-silicon verification is all perfect, everything, all the nook and corner of the design is properly verified, and once you manufacture chip, we can happily send it to the customer. But that is not the right thing, because during the manufacturing there are many things that can go wrong, right? So though your pre-silicon is properly validated, designed, right, for timing and physical point of view as well as logic point of view, everything is perfect, still there can be issue during the manufacturing. Okay, that if you can see in this picture, right. So even though you may generally you keep the manufacturing lab very clean, but generally there can be some things that are out of control, human control, right. So for example, here if you see, right, there is some dust on the wires of during manufacturing, where we generally do mask preparation, right. During that time, if there is any like because of this dust, right, those particles can cause the mask properly incorrect, actually is imperfect, right. If some dust comes and then there is a lithography that is going to pour the whatever the metals, right, and because of that dust that can make a broken wire, right, or if that is not a dust with some metal, right, that can cause short. So there can be many things that can go wrong during the manufacturing, and that is these are basic. Other things are, there can be issues in the precision of the manufacturing tools also, right, the lithography, or when you are creating the masks, right, because mask is also is a kind of cutting things, right, to make the image or to make the design put onto the wafer. So there can be impurities in the mask preparation as well, right. So any of these can cause the chip to be defective. Okay, so now that's where to identify all this, right, there should be a mechanism. We should test this. We cannot send the design to the customer after manufacturing just like that. It has to be qualified through third testing. Okay, that's where DFT is one of the important specialization which helps make sure that we are not going to send the defective parts to the customer, and which is going to cost very dearly, right, unless if you if you don't catch the problem, it will escape, and then you are going to see a customer return. Basically, that will be very expensive to the company. Okay. Now chip is manufactured, right? Now we want to test it, and after testing we want to send to the customer with qualifying, okay, nothing is defective, now you're good to go. But how are we going to test is the important topic for today's discussion. Okay, there are different ways. Okay, functional testing is one thing. Okay, and then is structural testing. We'll discuss about what is structural testing, but before that we want to discuss about functional testing. As we discussed in the pre-silicon verification stage, right, there are functional vectors that will be used during the pre-silicon verification. Okay, and generally because the chip will be so huge, and it is we will not be able to develop a test scenario where it's going to cover entire logic, right? And if you want to make such a vector, it's going to take many man months or man years also to design a robust test that can verify that can test the chip in silicon. Okay, that is one thing. Okay, and again that will only do the functional verification. It's not actually, it won't. Functional verification is if the test whatever we just now discussed is good enough, that is a perfect test. But generally, because of the inherent costs of developing such a test, that is not the right thing to do. One of the important aspect of that is, like, we cannot quantify how much percentage of the design you tested with that vector, because we don't know. Right now we don't have any mechanism to say, okay, right now how much of the percentage of design is covered by that vector. There are tools coming up to quantify the coverage, but even then, so designing such a vector is basically practically is impractical. Okay, so that's where the structural test comes into picture. Okay, so functional test, as mentioned, is going to verify the functionality of the design, right? Apply the test onto it, and it will do some the test is like a sequence of operation. Okay, and it's going to enable the logic inside, and then according to what are the sequence that we give, and it will give the response out, stimulus response out. Actually, the output we can compare. So this is generally happens in the functional test vector. Okay, the same thing if we can apply on the silicon, right? Post silicon, that is well and good, but that is what I just mentioned, right? So it is not, it's very impractical. Moreover, generally the functional vectors, the pre-silicon verification, they do lot of forces internal to the logic, because they don't want to control all the interface logic till the, for example, we are talking about the full adder, right? Full adder might be sitting somewhere low, deep in the hierarchy, and if you wanted to test that full adder portion only, somebody has to force the inputs on the ABC in, right? We have to force some stimulus on that, and then observe the output summary, sum and then carry, right? So that is all possible in the pre-silicon, because it's a gate level design. You can force on the inputs and inputs of the adder and observe the sum or carry through the internal observation, but that is not possible once the chip is manufactured, right? Because you don't have access to that logic in the manufactured chip, correct? So now what do we do, right? How do we control those inputs of this adder and observe the output of the adder? How do we do that, right? That's where the DFT comes into picture. So, and the DFT basically adds special logic in the chip, okay, that will ensure that we are able to control those inputs, whatever value you want to, and also we will be able to observe what is going to happen coming out of the logic. Okay, that is what basically the DFT intent is. Controllability and observability is the important thing. Okay. Now we talk about that again in the later slides, what are the controlled observability, but before going there, right, just want to explain what is structural test, right? Functional test we discussed, it is going to be verify the functionality of the block, right? For example, functionality of a full adder, it will have some inputs. If you make a truth table, if you have ABC input and the input, what is the output, summary and carry, you can see that is a functionality. But structural test will not do the functional verification. Actually, it will check in that example of the full adder, right? We have the XOR gates and then AND gate, OR gate, right? So it's going to structurally check whether that, for example, that XOR output XOR gate, whether it is getting the inputs properly, whether inputs are coming as intended, or they are like stuck with some value, or that is, and then output, we are going to check on the output whether output is properly coming as expected, right? So that is basically structural. It is going to check the structure of the design, targeting at the primitive level, actually, instead of the block level, and instead of verifying the functionality of the logic, right? It is going to check the basic primitive gates functionality to see that it is working as intended. Okay, it is going to apply different stimulus on the input side and see that output is coming as expected. Okay, that is called structural test. Basically, we are going to check. We are not going to check the functionality of the block, but we are going to check the structure of the logic, whether if the structure is input to the gate is proper, output coming proper, input of the gate, like for example, input is again, the gate is again part of the is made of a transistor, right? Whether the transistor performing properly, all those things are going to be checked as part of the structural test. Okay, for that we have different mechanisms. We'll talk in the next slides. Okay, so as we discussed in the previous slide, right? So any defect in the chip after manufacturing, right? That is modeled in a term called fault. Okay, fault is basically a abstraction of the physical defect. Okay, so there in the DFT world, right? There are different faults that starts with the stacked faults, transition faults, and memory specific coupling faults, right? These are different faults, and there are cell-aware. Now in the latest industry we are seeing cell-aware also. Basically it can go internal to the cell as well and understand the faults inside the cell, and then make the required test vectors to catch those defects. Okay, so basically this fault modeling is kind of a again abstraction of the behavior of the defect. Okay, so this is important that we need to understand, right? So the stacked fault is one thing which will basically, for example, we discussed, right? If the two wires, for example, if one of them is connected to a power supply, that is called stacked one, right? And let's say if it is connected to ground, because of, see how is connection happen, because of the manufacturing process defects, right? Either the wire can connect to the power supply or it can connect to the ground. When such thing happens, they'll manifest as stacked fault. Stacked 0 if it is grounded, stacked 1 if it is connected to the supply. So this is stacked faults. Okay, now comes the transition fault. What is transition fault? Is like slow to rise, right? Because for example, there is a wire that is coming as input to the AND gate, and another wire is coming to input of AND gate. Now the AND gate, let's say the two inputs are like one is 0, other one is 1. Now the output of the AND gate will be 0. So let's say assume initially in the previous cycle they were 1 1. Okay, output of the AND gate will be 1. Now one of the input goes to 0. Now it will be a 1 to 0 transition, correct? So now because of this, let's say the wire thickness, let's say it is so manufactured in a defective manner. Okay, instead of like a 3 mm thickness, it becomes like 2 mm, for example, right, or 1 mm. So that means when the thickness goes low, then resistance increases. So now the signal may transition slow. Instead of going as intended from 0 to 1, it will go 0 to 1, but it will go in a very slow fashion. That will result in the transition fault, because see, now we are talking about simple AND gate having this problem. Now between the two flops there can be multiple such AND gates. Okay, now if you have defects in these wires, right, all these small AND gates will accumulate the delay, and that final signal at the final gate before reaching the flop, it may come later than the 7th cycle. Okay, that is where this is manifest as a transition fault. Actually it is supposed to come before the next cycle edge, but because of all these delays, right, it will come after cycle edge. So that is good, we are missing the logic there, right? So that is nothing but a transition fault. Okay, and the third one is a memory coupling fault. As we discussed in the previous basic implementation of the memory, right, they are very closely coupled. All these sequential elements are closely coupled to meet the memory performance and area requirements. Now because they are so close, there can be proximity effect between the cell 1 to cell 2. Okay, and when the current goes to one wire, it may interfere with other adjacent wire, and that can basically make the whatever value in the other signal, other line can be coupled. Basically it will change its value because of the other wire. So that is all called coupling faults. So this is generally one scenario that we will see in the memories: coupling faults, adjacent coupling, column and row coupling faults. Okay, now we discuss about the stacked fault testing little in detail, right? So in this diagram, if you see, there is inverter. Okay, inverter will have one input and one output. When you give a 1 to one inverter, it will be 0. Is the inverter, right? So it is negated. It negates input. Okay, and so here in this fault model just now we discussed, right, stacked faults, for example, right? The input can stuck at 0, input can stuck at 1, output can stuck at 0, output can stuck at 1, right? Because whatever the physical defect that we just now discussed, any of these can happen. So that's why we call here, if you see A stuck at 0, A stuck at 1, A I mean like input A, I say output Y, okay, A stuck at 0 and A stuck at 1, Y stuck at 0, Y stuck at 1, okay, and these are the stuck at faults. Now the transition faults for the same thing will be A slow to rise, A slow to fall, same thing, Y slow to rise, Y slow to fall. So these are the terminology you can think of for the structural test, which is the stuck at test and the this transition test, okay. So as we discussed in the previous slides, right. So for structural tests, the controllability and observability is the important the parameter, basically how much controllable, how much observable you are in a design, that tells you how much you can cover, how much coverage, test coverage or fault coverage you can attain. So that's how the controllable observability is important for the DFT, okay. So here, as we discussed in the previous slides, right. So if you wanted to force any value on any gate inputs and want to observe the gate output, right. So first forcing is called controllability. You are not actually going to force any internal thing, but controllability means is how much ease you are at putting a particular node into the target value, because that is called controllability. Now once you make a once you attain the controllability, how much ease you have to observe the value in the external world, right, that is called observability. So yeah, controllability and observability are the the basic requirements in design for testability that will tell how much we are going to get the test coverage in a design. If you don't have much of this controllability, observability in design, then that's where we will not have proper coverage, and there is a chance for test escapes and then very costly custom returns and all the debug efforts, right. So to make sure that we don't get into those kind of problems, as part of design for testability implementation, we always ensure that okay, the stack should be more than 99% covered, okay, 99.9 and what generally target 99 above, and the transition fault coverage we keep generally 96 above. So if you make sure that these coverages are attained, right, there is a high chance that we are not going to deliver the faulty parts to the customer, okay. So that's the whole reason that this as part of DFT implementation we have to ensure that we have this controllability and observability taken care very well, okay. Now we will go to our core part of the present discussion, right, design for test, right. So similar to what we discussed on the chip design implementation process, right, it exactly follows the same steps here. So we have to once the design is like planned for implementation, okay, DFT has to plan basically what kind of test strategy you have to implement, right, and what are different components in the design that exist that you need to do testing, and if there are any already existing test mechanism available in the design, then how to integrate that into the system or chip level, right. Those are all planning we have to have in the beginning of the planning phase, right. Once you have the design intent and the component architecture information, everything, right, then comes the DFT architecture, right. So how you are going to verify, how you are going to test that each of the component is where we are going to define the DFT architecture, okay. Then comes the market architecture, like once you plan, okay, I am going to do this particular special component I am going to implement in a design, right, then comes how are you going to implement, that is going to be defined in the macro architecture definition, right. So as we discussed in the beginning, right, the logic, any design that contains IOs, it contains logic, the standards logic, it contains memories. Now all these components we have to test in such a way that we are going to catch if there are any defects in the manufacturing, during the manufacturing process. If any of these have got defects in the process of manufacturing, right, those need to be caught, so that we are not going to send the faulty chip to the customer. So that's why we need to have special test mechanism to cover the faults and the defects on the interface logic, right, pad boundaries, right, and then if there are any defects in the logic, combination elements or sequential element, if there are any defects in that, we need to have special test mechanism to test the logic, and then the logic memory test. So we need to implement a special strategy because there can be very different memory types. So each memory type may have different requirement to test. So we need to have proper strategy to test such memories. Okay, so that all happens during the architecture macro architecture definition, and this is also place where this architecture and macro architecture defines such a way that we are going to ensure that the coverage targets, the test coverage, the fault coverage targets we are but just now discussed, we need to attain those coverage numbers. This architecture definitions need to be very much very well defined, then only we can attain the target goals. So this is basically the cycle for DFT is a design phase. Okay, then once a test is like once a silicon, all the implementation done in the pre-silicon stage and verified everything, right, then comes the post-silicon. During the post-silicon testing, the DFT has to generate the test content, right, then that has to be delivered to the test team, so that the content stimulus can be applied on those components which are going to give that coverage, 99% coverage for Stuckert and 96% for H-speed, right. H-speed means like the transition test. So when you give such a quality content, we have high chance that we are going to catch all the defects in design, so that we reach the required DPPM. DPPM is like a defect per million parts, right. So there will be every design expected. Okay, it's not like once let's say 1 million parts are manufactured, it's impossible to have 1 million parts without fault, right. So but when you test it, we expect that at least out of 1 million part, we may miss our test, let's say 100 parts, right. 100 parts might escape because our test content, though you spent good amount of design implementation, right, to make the control observability everything inside, there is a chance that okay, there can be 1 or 2 nodes that may not be controlled observed, right, that will manifest as escape. So that escape could be, let's say I just mentioned, right, in a 1 million, if 100 parts are having escape, that is called, we have 100 DPPM. Okay, if the escape count is let's say 2000, right, for example, that means our test content, our DFT is not that robust to catch the defects that are happening in design. So which is going to manifest as like a test escape. Right now, after 1 million parts, 2000 parts went to the customer, which are faulty parts, and they are going to fail. System is going to fail, right? They are going to give a system customer return. That is like it's a bad quality test, because of that we are getting the customer returns, and after all the debug, because customer return, the system will fail again, they have to debug, right. So it's a lot of effort, they have to spend a lot of effort, time and money to make all this test happen, right. So that's where it comes to the DFT is where that comes into picture, right. The quality of DFT lies here only. If you can design a DFT which ensure that the robust content delivery, robust coverage, right, that gives you the good quality design, and we don't see customer returns. Okay, now we discussed that we have segregated the design into IOs and logic and memory. Now we will check how these components are tested as part of our DFT process. Okay, test in sense like we have to implement a design in the chip such a way that all this controllability, observability, which is the basic features of DFT attained. Okay, now we talk about this controllable observability. We can talk the same thing in the IO test and in the memory test as a logic test. Now we'll talk about the IO test, right. Okay, why do we need IO test, right? Basic thing. Let's say let's say multiple chips will be in a particular motherboard. There can be multiple chips, each of them are interconnected. Okay, now between the 2 chips, you wanted to see that they are all connected by maybe PCB traces, right. How to make sure that okay, now the PCB trace is not properly how to make sure that the trace is not trace is perfect. Like same thing what we discussed, right? It's internal to chip where we talked about the wires, right. Now we are talking about the wires external to chip also. Okay, now the chip to chip connectivity, for example, if it is broken or not, how do we check? That is taken care by this IO test. So basically IO test will ensure the pad we discussed, right. The pad contains the buffers, input buffer, output buffer, and then all the enable signals. If those things are properly implemented in the silicon, right, if they are not, to make sure that they are not defect free, right, this IO test is what is used. That is internal to the pad, but now it also tests the interconnect between the chip to chip also. For example, input is expected to be driven by one chip, and that is to be captured by the next chip, right, through this pad. If there is the trace is broken, now that is going to be caught by this IO test. Okay, that we call bound risk test. Okay, so basically there are various tests. Now we just talked about the structural defects in a pad and also the interconnect defects, right. And the third one also, like for example, what we talked about, the transition, right, the signal that is coming from the external world and coming into our chip, whether it is required that it has to go at certain transition level, at some slope. it expected to go, slope is also called slew rate. At what slew rate it is transitioning, right? To ensure that it is, because then only the incoming, the flop or logic inside the chip will capture that. If they are very slow, right, it will not be able to capture the signals as intended. So to ensure that it is coming at the right slew rate, that is tested by this characterization. During the chip pad characterization, those aspects of the design are tested, and that is also tested as part of this IO test. Okay. Now to make this test, IO test happen, we discussed that we need to implement some special logic. Okay. That special logic is basically the this boundary scan logic. Okay. And this boundary scan logic will be implemented as part of the 1149.1 protocol. Okay. This is the IEEE protocol. Because these chips what we talked, right, it can come from the different customers. The same one OEM which they manufacture the board to integrate all these chips for different customers, but unless they follow some standard, right, we will not be able to test chip to chip connectivity. So to make sure that these rules are followed, this is what the IEEE standard 1149 is what protocol each chip vendor has to follow when they design the chip. Okay. Then only we can make sure that the chip to chip connectivity is properly tested. Okay. That is IEEE 1149.1. Okay. Yeah. So I will discuss about it next slide. What is 1149.1? What it contains? Okay. It contains basic 4 inputs and 1 output. Out of 4 input, 1 is optional. TRST is optional. It is active low signal. TRST-B we call, but it is optional. Okay. So these are the 4 inputs and 1 output is what is required for this 1149.1. We call the test access port, that is called tab. Okay. And so it implements as we discussed in the beginning, right. So we need some interface to go program internals of the component that we discussed, and gate that full adder input, right. If we wanted to control some value into these gates, we are from external world, we need some test interface. So this is one such test interface. Okay. Through these pins, okay, with these 4 pins, it will have some test logic inside. Okay, that we call tap state machine. Okay, we'll say here, right. So this is basically is a finite state machine. Okay, that runs on the 4 inputs. Basically, out of the 4, one is a clock TCK, that is a clock, and then TMS is the mode select, which will basically switch between these states of this FSM, and then the TDI is what the actual data we pump in, what you wanted to basically program the component that we are going to implement in the interface in this tap FSM. Okay, this is one. Okay, this is one of the special logic. You can say test logic as part of DFT. This is the important component as part of the DFT infrastructure. Okay, so yeah, and if you I just wanted to show how where does this tap will sit, right, in this example what we discussed in the beginning, right. So in this chip we discussed the input pads are there, the green color pads, and then outputs are the violet pads, and then we have the standard logic and memories, right. So now to make sure that all the inputs are observed, because we wanted to what is happening from the external, what is coming from external world, if there is a defect or not on the external signal, right, the signal that will be observed in the circles. If those are circles are the boundary scan cells. Okay, and the inputs are observed in those boundary scan cells, and then because now you see the output pads, right, before they go out of the output pad, they will go through these boundary scan cells. This is the output boundary scan cells. Okay, now from basically input side we are going to capture into these boundary scan cells, and for the output cells what we are going to do is like we are basically giving controllable to the next chip, right. So we are giving a stimulus to the next chip to see that okay, the signal once passes from this output pad, it will go to the next chip, and next chip there will be input pad. That input pad will be capturing that data. Let's say in this process, if there is any defect in the chip to chip connectivity, whatever you sent, right, if you are sending 1, we expect 1 in the receiving chip that is not coming, that means something is broken. So that is caught during this boundary scan test. So if you see here, now all this boundary scan circuitry, it will be connected to this yellow box, which is the tap logic we just have discussed, right, the finite state machine, and it will have special logic inside. Along with this finite state machine, it will have something called test data registers. Okay, there will be multiple test data registers. One of the test data registers is like boundary scan. One of these boundary scan holds circuitry all chain you can consider or the test data register. Along with the test data registers, we will have some decoding instruction decoding logic, right? Different op codes, because boundary scan is one such instruction. There can be many such instruction to program anything else internal to the design. That could be one of the instruction. So this tab contains this final state machine is basically to make sure that whatever instruction you wanted to load into the instruction register are taken care, and it also contains the final state machine also contains the data path also. One is instruction path, other one is data path. I'll go here. One is the shift, if you see IR path, another DR path. So one is to load the instruction whatever you want to load into the trade. For example, boundary scan instruction is one instruction to enable the boundary scan test. Like that, if we can have another opcodes, two different purposes. So all that is done through these two branches of the state machine. Okay, now how it looks at the board, right? Now we just discussed. Now chip 1 to chip 2, there are 4 chips in this board. How they are connected, right? You see, they are connected through the interface connections between the chips, and if you see those small boxes, those are the boundary scan chains actually. And so boundary scan chain of one will interact with the boundary scan chain of another chip, right? And one chip will give stimulus to the other chip. Other chip can observe that and see that, okay, if there is any defects in the trace, other chip can also, when you shift out, you can see if there is defect or not, right? So here what are we doing? The controllability observability we are attaining through this boundary scan test. We are controlling the basically input to the next pad through the other pad. Okay, that is what control we are achieving, and from one pad output to the one chip output to the next chip output, we are observing in the receiving chip boundary scan cell. So basically we are attaining the controllability observability using boundary scan test between the chips. Okay, next, we discuss about now IO test. Okay, IO, I think we covered the basic intent of the IO test. There are many other things, for example, characterization, right? Multiple aspects of a boundary scan test are there, but we just discussed about the basic interconnect test. Okay, now we want to discuss about the logic test actually. Okay, because logic is also one of the very important building block of a chip. So now we wanted to cover how the standard cell logic is tested, right? So if you might have understood, there is a scan is one of the important technique that is used for the logic design for test. Okay, as the term implies, scan is basically like scanning the internals of a design without really going into the design, into the design. Basically, this technique will ensure that internals of the design are basically controlled and observed. Okay, that is the important of scan. We'll discuss how the scan looks like. Okay, and this scan can be in general, right? Design can be implemented out of flip flops, or it can be latch based on the functional intent and requirements, right? The design can be implemented as mux based flop or lower sense latch based. Yeah, if it is a regular, if it is a latch based design, right, then we need to implement a latch based scan test. If it is a regular flop based logic, then we have to implement a mux based. So each of them have their advantages, disadvantages. Okay, mux based design has, it will incur less area and low power, whereas LSSD based scan, it is going to take more area, but it will give timing performance. Okay, and so it's all this basically how the design is implemented. Based on that, we have to go with the strategy of or mux based or LSSD based. If your design is totally flop based, mux T is the technique we will generally use for scan implementation. So important thing, right? Yeah, if you take about a mux based design, right? So as we just now discussed, generally when the design is the sequential elements are flops, then we go for mux based. So if you see in this picture, right, a flop contains basic flop. It contains data input and clock, and it generally reset is optional, but it can be, there can be asynchronous reset also there. So reset and then flop Q output, right? In general, these are 4 pins. Generally, we'll have a flop will have. So this is basically when you really want to implement simple functionality without any scan, right? This is how it's going to be looking in the design, right? Now once you implement, if you want to implement scan, now this has to map to the scan cell actually. So left hand side is basically the regular cell without scan map, right hand side is a scan mapped cell, if you see, right? So when the cell, the flop is mapped to scan, it contains we are going to implement a mux on the D, right? That mux input will be one is the scan data, other one is the functional data, original functional data, and then select will be the scan enable. Okay, and the clock anyway will be controlled. We'll discuss about what is the specialty, about how to take care the how to control the clock as basic thing, right? For DFT, controllability observability is a very important aspect that applies to data as well as even the clock resets. Everything has to be controllable. Then we can make sure that whatever we wanted to write into the or force the value into the pins, that is attained, right? So that's what. So one functional flop is converted to scan flop. It contains the cell area will be more now because the mux is coming into path, and now if you understand clearly, since we added a mux, now the data to the flop is now little delayed because of mux addition. So that's where the timing performance will be little deteriorated in the scan once you implement scan. Area is one thing that is going to go up, and timing is going to be, there will be penalty. So we have to consider these aspects when we are basically implementing scan. When your physical implementation happens, all these things has to be taken care so that proper area is allocated to the design. Okay, if you see on the right hand side picture, it once the scan insertion happens, it looks like that basically. So let's say if the design has 100 flops, right, with the clock and reset properly controlled, now all those will be formed in a kind of a chain. One scan input will be there, one scan output will be there, right, and they will form a chain, and this is called a scan chain. Okay, so when you start a design, right, once you implement the design, RTL coding is done, right, then DFT comes into picture, and it ensures that all the clocks and resets are properly controlled. Okay, and once you ensure that proper clock and resets are properly controlled, and that is all done through the DRC, design rule check. Scan DRC is where we will check that, okay, every intended flop which we wanted to test, right, we expect that it passes scan DRC. If it's not passing scan DRC, means it will be excluded from scan and we are going to lose coverage, right. As part of the design implementation, we will ensure that, okay, we are going to attain this much, 99% flops are going to be scanned. Actually you can say 100% we need, but there will be some test flops which we cannot put them as scan, right, so they will be excluded. So but other than that, which are intended, let's say out of 100 flops in a design, 2 are test flops and remaining 98 are scan functional flops. Expectations all 98 flops should be part of scan. They should pass the scan DRC. So that's what we ensure actually as part of the design scan implementation. Okay, and so just now discuss scan DRC, right? Now and also we discuss about the clocks. How do we basically see data we are going to control through the scan chain, but now to ensure that the proper data is properly controlled, we need to make sure that clock is also controllable. Clock and resets are important things we have to have control during DFT. Okay, and so that's why the basic building blocks for a scan is we need to have a scan mode control logic. Okay, it will ensure that all these modes are properly controlled, and also we call something called on-chip clock controller, which will ensure that it's going to control the clock for that our intended test. Intended test is like stacked test is one thing, and transition test is another thing, right? To ensure that these two tests are properly done, the DFT need to have a controllability on the clocks. So this on-chip clock control is one of the important building block which will ensure that we can do the stacked and transition test. Okay, and at the same time now because we are adding logic to design, right, and the DFT has to be very mindful that our logic is not going to be too much that it's going to cause the chip, right. Any logic we add, it's going to cause some area into the design. Okay, and any logic we add into the functional path is going to be penalizing the timing as well. So DFT has to be very mindful, and it has to be so effective or optimized way that we have to implement our test logic. Okay, now one we have a technique called scan compression, right. We can instead of having, let's say if you have 1 million flop, right, and if you wanted to have scan chains of certain length, it will incur X number of scan chains. But if the number of scan chains are too huge, and if all of them have to talk to the external world, we need so many pads. Okay, but DFT is not the one. DFT should not ask for exclusively for the pads, because pads are designed for a functional application. For test purpose, the expectation we should not add pads, right. So that means what are the pads that are available, we have to use those pads to make sure that our scan chains are properly controlled and observed. So that is taken care through the compression logic. Okay, the scan chains, whatever, let's say you have some 1000 scan chains you have. Now all those 1000 scan chains data will be, the data that is coming to the 1000 scan chains will be compressed, okay, and given to the scan chains. Output from this 1000 scan chains will be compressed again in the compressor and will be sent out. So that is called compression logic. We will implement as part of the DFT. Okay, so this is where I think the picture of post scan implementation, right? The yellow block is where all this scan control logic, the on-chip clock controller or the scan compression logic or the scan sequence scan control logic, right? All this is going to sit in that yellow box, and it is going to interface with this all the standard cells and memories, so that to make them part of the scan. This yellow block is where it is going to control all these elements, so that the scan DRC is passed, right. Once the scan DRC is passed on these standard cells and memory also, right, it can also contain scan chains in them. So once we stitch all the scan chains into the scan control block and attain that, okay, all the flops and memory flops in the memory, not flops in memory, but the interface of the memory chains, right, if they are all properly controlled, right, that ensures that we have good coverage on the scan. Okay, now discuss the logic test we discussed, and then IO test we discussed, right, and then we discuss about the memory. Okay, in as part of memory, right, as we discussed in the beginning, memory is like a compacted version of group of flops put together to meet the performance and the area requirements, right. So because of that nature of the placement of those components, it will have its own special fault manifestation. The coupling is the important thing, right, and these memories can be of different type. One basic thing is a flop based. Simply you can imagine the matrix, right, let's say 100 by 100 matrix is a memory, that's 100 by 100, right, and we can implement with 100 flops and all the control logic. That is the simplest of thing. Simplest, you can imagine the simplest memory, that is called flop based memory. Same thing, they generally, right, smaller, if the memory size is, let's say I just give 100 by 100, but there can be memories of like 10 by 10 also, right. For 10 by 10 it can be simply implemented as part of flop based. But if you want some bigger memory, let's say 4K by 252, for example, if you such a big memory, right, then implementing in the flop based one will not yield the performance requirements. It basically it is so big block, right, and maintaining the timing requirement and based on the frequency, right, it is not it won't meet the performance requirement. That's why we will go to the macro. Okay, we are going to have a special cell now, that is called static RAM, or it can be dynamic RAM, or right, these are different. ROM or ROM, real memory is another category. So these are all various memory types, okay, in the industry that we generally use. Okay, based on the application, right, the static or dynamic RAM, it's all based on the application. What kind of application we can implement, either SRAM or the DRAM, right, or if it is a just read only, you just don't want to write anything, just wanted to load the image and just read it, right, that is read only memory. So these are different variety of memory that can go into the design. Now as similar to what we have the logic test and IO test, right, there can be defects anywhere in the manufacturing process of these components, right. Now how do we test these components is the memory test, because these are little specific, right, like these are very compact in nature, right, they have different fault manifestation, right, unlike the stacked and transition also will be here. On top of that there will be coupling also, because the cells are so close and so dense, right, there will be new coupling, another fault behavior can happen, that is a coupling behavior between the cells, right. So to make sure that those kind of defects are also taken care, we need special test logic, right. In the IO case we discussed about the tap logic and the boundary scan is one special logic. In the case of logic we discussed about scan, right, that is a special logic, scan and clock control, result control. And in the case of memory we have special logic called memory BIST, okay, memory built in self test. So we need that component as part of the design, we need to implement in the design, okay, for the memory test. Just want to show here how the memory look like, right. So as we discussed it, array of matrix kind of, the memory is where you can say the matrix based kind of analogy, but it's an array and it will contain the address, right. Memory is basically like rows and columns. Now if you want to access a first row, you have to give some address. I want to access the address 1, that means you need to give some address, and there will be a decoder, that is called address decoder, right, and that is nothing but column and row decoders, or like they are the constituents of address decoder. It will ensure that when you give the address, it will basically enable that particular row, and if you want to write into some that row, the data input is given, and then when the write table comes, it will write into that row, and when you want to read from that particular address, when the read table comes and read clock comes, the data will be taken from that particular row through sense amplifier down, right. So, if you see in this RAM, what you see, array is one part, address decoder, row decoder, column decoder is one part, and then we have the sense amplifier for the reading, to read the data out properly and send out, right, and then all the basically the control logic. So, these are the basic components of memory, right, unlike the standard cell. Standard cell is very simple flip flop with all the combo logic around it, but memory is like it is a special component with all so much complex logic inside. Now, how do we test all this, right? Scan cannot scan because it is a macro, right. Testing through scan is not a feasible solution, because already memory is very compact. We cannot add any scan, we cannot replace that with scan based thing, right, and scan is just, it will check the stacket and transition faults, but coupling faults, it needs it's not that robust. That's why we need a special technique called memory based. Memory based algorithms will be implemented in such a way that it's going to basically write into a row some value, and it knows that the controller knows what is the other row it has to write, so that if there is any coupling effect between these two, right, you can, when you read out from the intended cell, it can say whether the coupling effect is causing a defect or not. We can do observation in the, when you do MBIS test and observe output, we can check if there is a defects on this array. Okay, for that, to have proper controllability on those array elements, right, a regular scan will not help, and here is where the memory based control comes into picture with different algorithms. Okay, we have very different algorithms called March algorithms, and very complex algorithms are there now in the industry, which will go into basically controller target column or row cell, and also what is the basically the victim, possible victim cell, right. It can put some value into a adjacent cell, and to see what is the impact of this cell on the victim cell, it can basically observe. So, the algorithms are so robust that it can pump in all this data whichever is required to detect these defects, right. That based on the robustness of this algorithm, the quality of this memory test depends. Okay, just I want to give, I think we discussed in the previous slide, but this is, you can say, right, same thing what we discussed is like a row and column, right, and then all the address decoder logic, and then control logic and output logic, right. All these are basically the general simple structure of an SRAM, and defects can be anywhere. It can be coupling fault between the rows and columns, it can be for stacked faults in the address decoder logic, or it can be a transition faults in the sense amplifier. Anyway, these defects can happen. So, all this are taken care by the MBIS controller, because it implements a robust algorithm where the coupling between the rows and columns are taken care. Also, it can take care of the address decoder faults or sense amplifier faults or control logic faults. All these faults are taken care by the memory based controller. Memory based controller is kind of writing the targeted data into the memory and to the target address, and basically that is write portion, and it also reads intended, once you write, right, it can read from the same address and see what is written is coming or not. If what is written is not coming out, that means there is a defect in the memory. That is how it will be caught. Okay, this is the general pictorial representation of what I just mentioned, right. The BIST controller, it contains the address generator, data generator and comparator. Like address generator and data generator will pump the data into the controls and address and data into the memory at the internal location, and then control logic will go, and then once you write it, we want to read from those address location to see that whatever written is coming or not. That is going to be compared in the comparator, and if there is a mismatch, that's when we say okay, the test is failing, means like memory is defective. Okay, now this is a simple BIST control fast, right, but now how this BIST controller is controlled from the external world, external to the chip. Okay, that's where the tap will come to picture. So, one of the important interface is tap, other one is direct IO, but generally direct IO generally do not use, because there will be hundreds of memories or thousands of memories in design, and having interface, test interface for each of them is not practical, right. That is why they will all control through tap, test access port, what we discussed in the beginning, right. So, this is the MBIS architecture, right, generally so when the memories, if you see the right hand side, that is the memory. Just when you talk about simple memory, the memory interface is going to be controlled by the BIST controller, and BIST controller is going to be controlled by the tap. Okay. Now what are we doing here is, so to the memory there will be a functional interface already. Okay. Now we are going to, through the mux, we are going to mux the functional data through this BIST data, because the BIST controller now is going to generate this address and data, right. That data is going to be muxed with the functional data. So when you are in the MBIST mode, only the MBIST controller only will control the memory. Basically it will control the read write signals, it will control the clock, okay, it will control the all the read enable signals, and also output is taken, it will go to functional logic also, but it also come back to the BIST controller, because we have to compare data what is written, right. So that's where the comparator comes into picture. Okay. And here, so this MBIST controller, just want to give a little more basics, right. It can have, it's not like one controller will have one memory, we can give more than one memory also. It can group the memories based on the clock, basically what kind of, because every BIST controller is testing the design at the rated frequency, it's not a test frequency. Let's say if the memory is running at less than 900 megahertz, right. So the BIST clock, the functional clock is going to come to the BIST controller, and it will go from there, it will go to the memory, right. So that's why the BIST controller, whatever we are implementing, right, all the memories of the same clock can be grouped into the MBIST single controller, just to save the area, because we don't want to have one MBIST controller for every memory, right. As part of DFT MBIST implementation, we can group the memories based on the clocking is one thing, and then the area requirements also, and the test requirements. Based on all these requirements, we do generally group the memories, so that we attain the test area requirement, at the same time test time requirements, right. Considering all these aspects, these memories are grouped under a corresponding MBIST controller. And MBIST controller, there can be like hundreds of MBIST controller to serve the thousands of memories in design. All this will be connected to the external world through the tap network, right. So now if you wanted to write any content into the memory, if you want to write some data into memory through tap sequence, it will control the BIST controller. BIST controller will enable the trigger algorithm. The algorithm will write in some data into the memory, right. It can read from memory. Once the data is read, it will be MBIST controller will send the data to the tap, and from the tap we can see the data at the external world. So that's how the connectivity happens in the design to the memory till the external world. So here also, if you again recall, right, controllability and observability, the important theme of the DFT, which you are attaining through all this means. So for all we discuss IO test or the logic test or the memory test, controllability and observability, the important theme of DFT, and these are different strategies we use how to attain this important theme, controllability and observability. In the case of scan, in the case of logic test, we are attaining through scan. In the case of IO boundary scan test, we are attaining through the boundary scan logic, and in the case of MBIST, we are attaining through the MBIST controller and this tap network, right. So that is basically the overall, like how we test the edit design or different components of design, right. So I just want to discuss about summary, right, for the design for test. So the goal of design for test is basically the quality, right, and attaining the quality at the lower cost. That is basically the strategy that any DFT engineer has to keep in mind, right, because quality is at most important, at the same time because cost is also very critical to make the business viable, right. That's why we have to take care of the design as well as the test cost requires to be consideration. Okay. And I just want to mention about this DFT is a structural test. It's different from the functional, right. Functional is basically we are going to test the functionality of design, but the intent here in DFT is a structural test, where we are going to focus on the internal primitive component level and then ensure that we test those structures properly. So that's why it's a structural test. Okay. And as we discussed multiple times in this presentation, controllability and observability are the important key themes of the DFT. How much you attain these two things into consideration or achieve this, that tells you the quality of your DFT. Okay. And last one I just want to mention, okay, DFT is a very important a specialization in the VLSI design, and it ensures basically the overall business of the chip, right. If you make sure that it is with very less area and with low cost, if you can implement the design, you will get more margins from the silicon process, right, and the profit margins are all based on the design. Test is one of the important aspects. That's where it depends. Basically, if you can test it with low cost, that the margins will be good. And so other important thing is that DFT is basically where it will start from the beginning, right, from the product conceptualization till it goes to production, and then it comes back if there are any customer returns. Throughout the whole cycle, DFT will be part of the process. So that's why it's a very critical and niche field, and we need more resources in this field right now. Thank you for this.